I'm Shami Chatterjee. I'm an astronomer at Cornell University, and I'm a member of the Nanograv collaboration, which is how I know Sarah Vigeland. Sarah is a brand new assistant professor of physics at the University of Wisconsin-Milwaukee, and she is also at the Center for Gravitation, Cosmology, and Astrophysics, where she studies gravitational wave astronomy with pulsar timing arrays. She is a member of the Nanograv collaboration, as well as the International Pulsar Timing Array and the LISA Consortium. And today she's going to give us a brief introduction to science with pulsars and magnetars. So Dr. Vigeland.
Yeah, so this is a very broad topic, especially as I'm going to discuss in my talk, and as my title says, pulsars are actually both targets and tools for multi-messenger astrophysics. So I'm going to try to talk a little bit about both aspects, but I'm definitely biased towards talking about them as tools because that's what my research focuses on. Okay, so most of you are probably familiar with what pulsars are. Pulsars are rapidly rotating neutron stars that emit beams of radiation. And as they rotate, the beam sweeps around like a lighthouse, producing these regular pulses of radio waves. By timing these pulses, you can measure the properties of the pulsar and its environment very precisely. For example, the first evidence of gravitational waves came from pulsar timing observations of a binary pulsar, B1913 plus 16. Over the course of about a decade, it was shown that the binary orbit was decaying due to the emission of gravitational waves. Of course, recently, we had the first direct observation of gravitational waves from a binary neutron star, although not a binary neutron star where the two stars are just slowly orbiting one another, but one where the orbit has decayed to the point where the two neutron stars merge. Okay, this, of course, this was a very exciting event, not just because of getting to see the gravitational waves, but because it was also seen in a number of electromagnetic telescopes. It was a huge triumph of multi-messenger astrophysics and yielded a wealth of information, including providing evidence of a connection between neutron-star mergers and short gamma ray bursts. Now, since then, LIGO has observed many other compact binary mergers, including some that involve neutron stars or potential neutron stars. For example, this recent discovery where one of the progenitors is in this mass gap between neutron stars and black holes. So it's either a very massive neutron star or a very light black hole, or I suppose it could be some new kind of compact object. And this mass gap is very interesting because the maximum mass of a neutron star ties into the neutron star equation of state. Okay, so this plot shows lots of theoretical neutron star equations of state, and you can see they all predict different maximum masses. And the horizontal lines indicate masses of massive pulsars, which are measured through pulsar timing observations. There was a recent publication of a very massive neutron star, possibly the most massive. The neutron star masses can be measured through something called the Shapiro delay, which is a relativistic time delay caused by the pulses of the pulsar propagating close to the companion object. In order to measure Shapiro delay, you have to have the orbit lined up just so, otherwise the pulses don't pass by the companion. Okay, so this was a paper led by Thankful Cromartie and Emmanuel Fonseca. But I actually want to talk mostly about pulsars as a tool for doing multi-messenger observations of other types of sources through pulsar timing. Pulsars are extremely stable rotators, which makes them ideal for detecting low-frequency gravitational waves with periods on the order of years. Some pulsars are stable over periods of decades, over the timescale of decades, which is really amazing. And so pulsar timing arrays take advantage of this property by using them to search for gravitational waves. The way you do it is you look for correlated changes in the pulse times of arrival between different pulsars. You need an array of pulsars because if you see something in the residuals of a single pulsar, it's very difficult to say if that's actually due to a gravitational wave versus something that's just intrinsic to that pulsar. But if you see a correlated change in dozens of pulsars that are separated by kiloparsec, then you can be confident that this is produced by gravitational waves and not some kind of other astrophysical effect. There are a number of pulsar timing array experiments going on right now. I'm part of NanoGrav, which stands for the North American Nanohertz Observatory for Gravitational Waves. We're made up of about 100 scientists and students spread out over the United States and Canada. And we primarily use the Green Bank Telescope in West Virginia and the Arecibo Observatory in Puerto Rico. We've also started incorporating data from the VLA and CHIME as well. There's also a pulsar timing array experiment in Europe, the European Pulsar Timing Array, and one in Australia, the Parkes Pulsar Timing Array. And all of these groups operate under, collaborate under the umbrella of the International Pulsar Timing Array. There are also a number of what we call emerging PTAs in South Africa, India, and China, who are just getting started with their own pulsar timing array experiments. It's very important that we all collaborate internationally because pulsar timing arrays are more sensitive if you have more pulsars and if you observe for longer and at a higher cadence. And so by combining all of our data together, the combined data set is more sensitive than the individual PTA's data sets. The primary sources that pulsar timing arrays are sensitive to are supermassive black hole binaries. You're going to be hearing a lot more about them tomorrow from Sarah Burke-Spillauer, but just briefly, supermassive black hole binaries form when galaxies merge. Initially, the evolution is dominated by environmental effects, but eventually gravitational wave emission takes over. Pulsar timing arrays are sensitive to the gravitational waves emitted when the binaries, when the black holes are separated by less than a parsec, but they're still evolving relatively slowly, certainly slow compared to a human lifespan. And so we often refer to these sources as continuous waves, even though they are not technically continuous, they are evolving slightly. Eventually, the gravitational wave emission will cause those two black holes to merge. The oscillatory part of the merger cannot be seen in PTAs. It's at too high frequency, but it can be seen by space-based gravitational wave detectors like LISA. PTAs, though, can see the DC offset. If you notice on the very far right of this diagram, the line it's up a little bit from where it is on the left. That's not just an error, that is a real effect. It's called the gravitational wave memory. Okay. Now we expect that the first gravitational wave source that PTAs will see is the stochastic gravitational wave background, which is made up of gravitational waves emitted by all of the supermassive binary black holes in the universe. There's a lot of astrophysics you can learn about supermassive binary black holes as a population from characterizing the background. The amplitude tells you about things like the mass distribution of supermassive black holes and the merger timescale for galaxies. The shape of the spectrum is connected to what's driving those binaries to merge. So if they are all evolving only due to gravitational wave emission, then the characteristic strain spectrum should follow an f to the minus 2/3 power law. But if the evolution is dominated by environmental effects like stellar hardening, then the strain spectrum will have a different slope. And where you go from being environmentally dominated to gravitational wave dominated, you have this turnover. Okay. We're also sensitive to gravitational waves from individual supermassive binary black holes. So even though we haven't made a detection yet, we're already able to put limits on nearby binaries. On the left, this is a This is a limit on nearby supermassive binary black holes from an analysis of the NanoGrav 11-year data set. So here our sensitivity is cast in terms of a lower limit on the luminosity distance to nearby binaries. So at our most sensitive sky location, we can say that there are no binaries with a chirp mass of 10 to the 9 solar masses within 120 megaparsecs. And if you consider 10 to the 10 solar masses, you can say there are none to 5.5 gigaparsecs. Okay. We can also look at, so these limits are just for the sky overall, but we can also look at specific promising candidate supermassive binary black holes that have been identified from electromagnetic observations. So for example, 3C66b was first proposed as a binary back in 2004, I think. And soon after, it was shown that if it did have the mass initially reported, it would be generating such loud gravitational waves that you would be able to see them in the residuals of a single pulsar. Since then, the mass estimate has been revised downward. Recently, we used the NanoGrav 11-year data set to place limits on the chirp mass. This is the first time PTA data has been used for this purpose. It's the first analysis using many pulsars instead of a single one. This was work led by Caitlin Witt, who's a graduate student at West Virginia University. And it has been submitted to the journal and it's on the archive now. We can also put constraints.
3 minutes, Sarah.
Oh, thank you. We can also put constraints on nearby galaxy mergers. So this is in an upcoming paper, which is being led by Maria Carisi, who's a postdoc at Caltech. We use, again, the NanoGrav 11-year data set to put constraints on the mass ratio of potential supermassive binary black holes in the local universe. And the reason this is interesting is that major mergers of galaxies involve two galaxies of similar masses, and so the resulting binary will have a large mass ratio. So if you can say that the mass ratio is below that limit, you can say that there hasn't been a major merger. Okay. Okay, so in conclusion, pulsars are in my mind a particularly interesting astrophysical source. They've been used for all kinds of interesting science, and the era of multi-messenger astrophysics promises even more interesting results because they are both targets and tools for multi-messenger astrophysics. As we've already seen with the LIGO discoveries, with the LIGO detections, we've been learning a lot more about neutron stars from being able to observe neutron star mergers. That's only going to increase in the coming years. At the same time, pulsars are being used to detect, to search for low frequency gravitational waves. And once detections are made, we'll be able to use those pulsars to study supermassive binary black holes in a way that's complementary to electromagnetic observations and will help us learn a lot about the population of supermassive binary black holes and galaxy mergers. Thank you.
Thank you, Sarah. Thank you very much. We do have time for a couple of quick questions. One of our listeners, viewers asks that LIGO Virgo discoveries clearly show that the mass gap is not actually empty. Can you comment on any selection effects from the EM side that might have resulted in a lack of objects in this gap?
Oh, okay, that is really outside of my area of expertise. I mean, yes, you make a really good point. I mean, we have found things in the mass gap, so they are out there. As to why we haven't seen them with electromagnetic observations, honestly, I don't know. Yeah, I mean, I think that though that's a really good, that's why multi-messenger astrophysics is so exciting, is because now that we can see gravitational waves, we're seeing all kinds of things that we can't see electromagnetically. And that's not a surprise, because the same is true if you think about only being able to see in optical versus being able to see in optical and radio and X-ray. But yeah, I don't know. I think that's a really interesting question though.
One other quick question. We have a question which is, do the current upper limits by pulsar timing arrays lead to constraints for LISA?
Oh, that's a really good question. So I would, let's see. Let me show this plot. Yeah, so, oops, okay. I already exited. Well, okay. Right, okay, so you can see my conclusion slides. Right, so yes, so the binaries that we see in LISA will eventually, or the binaries we see in PTAs will eventually merge and become binaries for LISA. But but the ones that we see are very, very massive, whereas LISA is able to see much lower masses. And so I think the ones that we see are actually a small part of the population. That being said, you know, the ones that the lower mass ones do merge and eventually become the really massive ones that we see. So there is definitely a relationship between those two populations, but I think that it's rather complicated.
Thank you again, Sarah. I think we will move on from here.